Here we go.
Hey everyone, welcome to this DNTF session based on leaf integration with UPF, that is user plane function of 5G core. In this session, we will be going through a brief intro about UPF, what UPF looks from inside. We will explore some options to improve packet path to UPF, and we will also introduce you to DPDK and XTP and the limitations. Then I will take you through the integration of UPF with leaf and its future scope in it. So this is the main topic of discussion today, that is leaf integration with 5G core UPF, that is user plane function. Now let's move on who we are. So I am Shankar and I am a research engineer at NG Core. So NG Core is a research and academic based community dedicated to exploring innovative solutions to complex challenges in 5G and 6G technology. NG Core has been tirelessly exploring innovative solutions to the complex challenges in field of 5G core, Open RAN, software defined radios, network function scaling, user plane scaling, packet acceleration, eBPF and cloud technologies. NG Core is also an umbrella organization for some well-known entities like Magma India, OIP Labs, OpenStack, etc. And together we have successfully tested and deployed a comprehensive end-to-end 5G system utilizing a range of open source projects as well as our in-house developed solutions. We have even tested this with the cores like Magma, OAI, Open 5GS, Free 5GC and SD Core. So we are also associate members of Magma Foundation, Open Infra Foundation, Open Air Infra, Hyperledger, and recently we have partnered with Meta and Linux Foundation on LF connectivity at university level for project like TerraGraph, OpenMplane and Mavic. Now let's move on what UPF is. So UPF is a user plane function that plays a vital role in the 5G core network architecture. Its primary responsibility is to perform packet processing and enhance forwarding policies for user data traffic. Essentially, it ensures that data packets are delivered to their desired destination based on the policies and quality of service requirement defined by the service providers. One of the key functionality of the UPF is to handle traffic management, which include packet inspection, filtering and even deep packet inspection called as DPI. These capabilities allow the UPF to analyze the contents of data packets, making decisions based on specific criteria defined by the network policies. For example, the UPF can filter out unwanted or malicious traffic, ensuring the network security and integrity. Moreover, the UPF serves as a critical component in enabling advanced 5G features such as network slicing. Now, here is the UPF architecture. Let's explore the architecture of UPF, and it includes two layers of UPF. The first one is the PFCP agent and the second one is the data path. So these two layers work together to enable seamless communication between mobile core control plane and the data plane. The first layer is the PFCP agent, which is a Go-based implementation of PFCP northbound API. It acts as an interface between the mobile core control plane and the UPF, allowing the exchange of control plane messages such as session establishment, modification and termination. The second layer is the data path, which is our concern for the session to enhance the performance of UPF. So data path is responsible for the actual data plane packet processing within the UPF. By integrating eBPF into the data path, the UPF gains several benefits. It can efficiently process packets at the high speeds, implement custom packet filtering rules and perform complex operations directly within the data plane. This integration of eBPF within the UPF empower network operators to optimize performance, enhance security and add new features to the UPF deployments. So the PFCP agent implements data path plugins that translate PFCP messages to the data path specific configurations. We currently support two data path implementations. The first one is BESS, a software defined data path built on top of the Berkeley extensible software switch framework, and the another one is the UP4, an implementation leveraging ONOS and P4 programmable switches to realize a hardware-based data path. The combination of PFCP agent and UP4 is usually referred to as P4-UPF, while best UPF denotes a combination of PFCP agent and the best data path. Now, this is a diagram showing the UPF in the 5G architecture. As you can see, the UPF on the right hand side is connected to the data network through the N6 interface, and on the left hand side it is connected to the G0B, that is a RAN part, through the N3 interface, and through the N4 interface it is directly connected to the core. As you can see in the image, it is connected to the SMF. Now UPF has its own advantages and it is very versatile in nature. Some of the key points of UPF is it basically allows QoS handling, policy rule enforcement, packet inspection, inter and intra-RAD mobility anchor, etc. Now, so here comes our old friend DPDK, which is an option to express the data path towards UPF. Let's explore how DPDK enhances the performance of UPF. So DPDK is a set of libraries and drivers that allow high-speed packet processing on x86 platforms. By leveraging DPDK, UPF can achieve significant performance improvements in handling network traffic. However, it is important to note that DPDK has hardware dependencies and supports only specific NICs. While DPDK brings substantial advantages, integration with non-DPDK apps is a bit challenging in it. So now comes a better option in terms of hardware compatibility, that is XDP, also called as Express Data Path. So XDP allows for efficient packet processing within the kernel space of the operating system. Unlike bypassing the kernel entirely, XDP operates as an in-kernel fast path. This approach offers the benefit of improved performance while retaining the advantages of kernel level functionality and compatibility. One of the key advantages of XDP is its ability to perform packets processing without dedicating full CPU cores solely to this task, as in the case of DPDK. This means the UPF can leverage the CPU cores more effectively, allowing for a more balanced utilization of system resources. Now we have some limitations of XDP. So one of the limitation of XDP is the limited program size. XDP programs have a restricted size constraint, which can pose challenges when implementing complex packet processing logic. Now, managing multiple eBPF programs, XDP programs can also be a bit challenging here because it does not support managing multiple eBPF programs. Additionally, XDP lacks a built-in mechanism for monitoring and capturing matrices for XDP programs. This makes it challenging to gather insights into the performance and behavior of the program. So we need a solution to it, right? So let's go through the solution. So here Leaf comes into play. So as I already told you about XDP and DPDK, so now you are aware about pros and cons. So for the solution, we have Leaf that can perform most of the tasks that XDP and DPDK lags behind. So here is the Leaf that do complete lifecycle management of eBPF program in the kernel. Let's have a look on its architecture and advantages it offers. So it is the Leaf architecture, as you can see. Now, and this is a representation of fully functional architecture with all the components included in it, and let's have a look on how it basically works. So the process starts when a user makes an API call. This call sends configuration data to deploy eBPF kernel functions on the kernel at both XDP and TC levels. The configuration data from this API call is converted into specific policies. These policies are then stored in a database for further reference. The leafd retrieves this stored configuration data from the database. It does so by using a key value pair stored in the KV store. This allows for quick retrieval of the relevant policies from the database. Once the configured data has been retrieved, the leafd downloads pre-built eBPF programs from a user configured repository that they call as eBPF package repository. These programs are contributed by a diverse community of developers, and each program is verified before it is installed in the KV store. So the leafd is the main component of leaf control plane. It manages and orchestrates multiple eBPF programs and runs on each node where the user wishes to run the eBPF program. The leafd loads these downloaded eBPF programs into the kernel. As they are loaded, their file descriptors are stored in a previous kernel function map. This keeps track of the sequence of programs that need to run in the process. One important thing to note here is that the NIC only needs to know about the first eBPF program in the sequence. The remaining programs are called in order through a function called as BPF tailcall, which uses the file descriptor stored in the current program's map. Each packet is processed through each eBPF program in sequence and then passed on to the network stack for further processing. Finally, the processed packet is sent to the destination application for any additional necessary processing. The Leaf project currently manages eBPF programs operating at XDP hook and the driver and the TC ingress hook at the initial step of the kernel network stack. The network packets from the internet undergo processing at both XTP and TC levels, after which these processed packets transmit the remaining layers of network stack for further handling. Now here are some of the points that Leaf can do but XTP can't. As you can see here, Leaf can orchestrate and manage multiple eBPF programs. It can also be used to monitor the programs using Prometheus query language and Grafana, and it also used to attach multiple eBPF programs from different sources, like from their eBPF package repository or from third-party vendors. So now we have the main topic of discussion, that is UPF with Leaf. So let's move on and try to see the logic behind this concept. If you have a look on the diagram, here the packets processed from the leafd will move toward the core interface of the UPF. At this junction, the base UPF processes the packets, preparing them to be transmitted to the destination via the access interface. In return path, the packets travel back to the NIC following the same trajectory as the incoming path. This cyclical process ensures that data packets are effectively and efficiently processed, promoting robust and reliable network performance. This setup enables high performance flexible network management, fostering increased efficiency in data packet routing and processing. However, there is a limitation with the current setup where packets passed by the Leaf eBPF programs can't be passed to the UPF due to the absence of suitable socket in the network stack. So as a result, these packets are lost, and to address this issue we have implemented AFXD socket. So this allows the passed packet from the Leaf to reach the UPF in the user plane. So as you can see in this image, we have implemented AFXDP socket in order to move the packets from leafd to the UPF. We are currently undertaking efforts to integrate AFXDP socket with the UPF and the XTP, forging a seamless pipeline for packet processing. The integration of AFXDP is intended to streamline the process by which packets are managed within the network. Under this new configuration, packets are first processed by the XTP. Following this initial step, they are directly passed to the UPF, and this handoff is facilitated through the AFXDP socket. Right. So this approach crucially bypasses the kernel, enabling a more efficient route for packet processing and minimizing system overhead. The packets are then transferred via the core interface, where they are subsequently processed by the base. The goal of this integration is to optimize network performance, creating a more direct and streamlined path for packet routing. By leveraging the capabilities of AFXDP for kernel bypass, we aim to increase efficiency and reduce latency in the network, thereby improving overall network functionality and user experience. So here are some advantages of leaf that you can see on the screen. You can go through these, and now we also have some future plans with leaf that can be implemented in future. And these basically include, like, leaf can be used to orchestrate multiple eBPF program to enhance UPF functionality, and that also result in efficient packet processing and improved network performance in UPF. Along that, UPF also provide horizontal and vertical scaling options which can be considered as per future demand, and it also allow deployment of multiple UPF with multiple eBPF programs. So moving forward, our primary objective is the transformation of UPF logic into eBPF programs. The intention behind this endeavor is to bring these modules under the management and orchestration purview of the leaf system. Currently, we are undertaking significant strides in integrating leaf XTP socket, AF XTP sockets with the UPF and XTP. This enables a streamlined pipeline for packet processing that enhances network efficiency. The planned transformation of UPF logic into eBPF programs complements this setup. By doing so, we aim to extend the flexible, efficient management capabilities of leaf system to the module currently under UPF logic. This strategic initiative represents an important step forward in network packet processing, fostering improved network performance and user experience. So overall, these developments signify a bold reimagining of our network architecture, leveraging cutting-edge technologies such as eBPF, AFXCP, Leaf for optimized network management. Now let's move on to another use case that we can achieve from Leaf, that is horizontal and vertical scaling. So in horizontal scaling, Leaf can be a key component in managing horizontal scaling by coordinating the distribution and execution of multiple eBPF programs across multiple UPF nodes. When a new node is added to the system to handle increased traffic, Leaf can ensure that the correct eBPF programs are loaded into the kernel and running on the new node, maintaining consistent performance and functionality across all the nodes. And in vertical scaling typically involves the addition of more resources to an existing node, such as more processing power or more memory. In this scenario, Leaf can contribute by efficiently managing and orchestrating the execution of eBPF programs within the expended resources. Leaf can optimize the use of these additional resources, ensuring that the eBPF programs utilize the extra capacity effectively to handle increased traffic. Furthermore, the observability provided by eBPF and Leaf can be used to monitor the system's performance, helping to determine when vertical scaling might be necessary. So, however, it is important to note that while Leaf and eBPF can contribute to the efficient use of resources and can help facilitate scaling, they do not involve themselves handling the scaling. The actual decision to add more nodes or increase the resources of nodes would generally be handled by other systems such as Kubernetes or OpenStack. So Leaf and eBPF play a role in ensuring that the scaled resources are used effectively. And this one is more important use case of Leaf. So what we can do in this, we can deploy multiple eBPF programs along with multiple UPFs respectively. So this could be good use case, as Leaf will be there over the UPF to manage, orchestrate, monitor and attach multiple eBPF programs. And yeah, this is all what we have achieved, and we have tested Leaf with our UPF along with the AFXCP socket. Along that, we have already tested UPF with Leaf with the UPF of SD core, and the results were good. So, and we have already seen better performance after integrating eBPF and Leaf, and a team of researchers is already busy in writing UPF related eBPF programs. So yeah, So these are some sources from where we have taken the data, and yeah, if you have any query you can reach out to us using the mail, and we will try our best to provide you the solution. Thank you.
Thank you, Shankar. Any questions? Okay. Thank you again. Good session. The recording, let me stop the recording.